problem 2. For problem 2, we will have a circuit with a battery, plus minus V. Then we will have here a switch. We will call this point A. And then we will have a resistor with resistance R. Then we will have an inductor here with inductance L. And we will close the loop. Let me do it better. We will close the loop this way. And we will have another switch here. We will call this point point B. Now, the switch was in position A for a long time. Position A, so here is the switch, and we put it either in position A or in position B. The switch was in position A for a long time. I put it in position A. For a long time means that steady state was reached. Then, after that, the switch was moved to point B. After that, the switch was moved to point B. What we are looking for? We are looking for current in this circuit as a function of time. The first question, which law will we use? We will use Faraday's law to figure out what is current as a function of time in this circuit. So let's write Faraday's law. It tells us that integral E dot dr over closed path is equal to minus d dt of the flux of the magnetic field, B dot ds. What I have here is the flux of the magnetic field, and we call it phi. Phi is integral B dot ds. Well, first of all, the switch was in the position A, and it was in the position A for a long time, which means that steady state was reached. So let's find the current in steady state through this circuit. We follow our steps. The direction of current, let it be clockwise. It is leaving positively a positive terminal of the battery. Then we have a resistor here. It is steady state. For steady state, I have the right-hand side of Faraday's law 0. No time dependence. Steady state d dt is 0. So we work with the left-hand side of Faraday's law, and we follow our usual steps. The direction of current, then direction in which we go around the loop. We will go around the loop in the counterclockwise direction, which makes ds out. You use your right hand to find out direction of ds. If you go in counterclockwise direction, you bend your fingers in counterclockwise direction. Your thumb shows you the direction of ds. It is out. And now I go around the loop. We go in counterclockwise direction. So when we go across the battery, we have negative change in voltage, which means positive change in E dot dr. So I put plus V. Then we keep going. There is no time-dependent process since it is steady state. So this is just a piece of wire. We ignore this inductance. Then we come here to this resistor. Current is going in clockwise direction with our choice, and we go in counterclockwise direction. So this is direction of current. Electric field, that is rho J, is also to the right, and we go to the left, which makes E dot dr across the resistor negative. I put minus, and magnitude is IR, and we come back to the battery, so we close the loop. This is our equation for steady state, and we immediately solve for current. Current is V over R. After that, the switch was moved to the position B. Let me draw it. Now the switch is in position B, which means that this part of the circuit is non-existent. We have a gap here. Current cannot flow. We have closed loop only here. Let me redraw this circuit, and by redrawing I mean that I will just erase this part of the circuit since we put the switch in the position B. So I erase this part. It is irrelevant now. We have current flowing in this circuit that we already calculated. Current at time moment 0 when we brought the switch to the position B was IV over R. I put that as our initial condition. Current at time moment 0 is V over R. I will use Faraday's law to find out current as a function of time. And now I will erase steady state since we don't need it anymore. And we will work with Faraday's law when we have the time-dependent process. We have now non-zero right-hand side of Faraday's law. We still have our inductor here. And instead of 0, we have minus d phi dt, changing flux of the magnetic field. So what is phi? We need to make our choices and we need to follow the steps. What are our usual steps? We again will go around the loop in the counterclockwise direction, which means ds is out of the page. Then I have current in clockwise direction, which makes you use your right hand. You use your right hand. I use my left hand, ironically, because you see my mirrored image. So I bend my fingers along current, and my thumb shows me the direction of induced magnetic field. So B induced by this current is into the page. This is B direction of the magnetic field. Now B is in, ds is out, which means that B dot ds is negative, flux is negative. Phi is plus minus Li when we have inductance in our circuit. And since B is anti-parallel to ds, dot product is negative, we choose minus. It is minus Li. Next step, let's take derivative, d phi dt. d phi dt is minus L di dt. Now we are ready to work with the left-hand side of Faraday's law. We go around the loop. Current is to the right, and which means that electric field rho J is to the right. We move to the left around. We go around the loop in counterclockwise direction, which means dr is to the left. E is anti-parallel to dr, dot product is negative. I put minus. Magnitude is IR. This is the left-hand side of Faraday's law, and it is equal to minus, this minus from Faraday's law, and then d phi dt. And d phi dt is minus L di dt. Minus minus plus, I have here L di dt. And now let me bring this guy to another side of the equation and see, or this guy to this side of the equation and see what happens. So I have L di dt plus Ri, and this is equal to 0. I can divide by L. It's not necessary, but I like to do that. Di dt plus R over L I is 0. And now look at this equation. It is first order, linear, homogeneous differential equation. We know what to do. We already solved this equation in our previous problem. Again, if you know how to solve this equation, you can use the method that you like. I will use the same method as the textbook uses, which means that I will guess the solution. And it will be educated guess. I'm looking for my solution as alpha, that is unknown constant, times exponential function to minus, this minus is crucial, minus beta, unknown constant, beta t. I need now to find alpha and beta. First of all, I will find beta. How to find beta? I take my guess, my solution for current, and I bring it back into my equation, which means that I need to find di dt. What is di dt? I differentiate I get alpha, constant, then exponential function e to minus beta t, and chain rule gives me minus beta. So it is alpha minus beta e to minus beta t, we are right here, plus r over L, I, which is alpha, e to minus beta t, and this is equal to 0. Next, let's simplify this. I divide both sides of equation by alpha and by the exponential function, and I have now minus beta plus r over L is 0, which brings me to beta as r over L. We found beta. Next, I need to find alpha, and I will find alpha from the initial conditions. At this point, my solution looks like, let me write it here. My solution looks like current as a function of time is unknown constant alpha times exponential function minus t, beta, I forgot beta, and beta is r over L, minus r over L t. I will bring t here, minus r over L t. Now let's find alpha. How do we find alpha? We find alpha from the initial conditions, and this is our initial condition. So current at time moment 0 is equal t0, exponential function to 0 is 1, I have alpha. And at the same time, we know that it is v over r. So alpha is equal to v over r. We found alpha. Now we know current as a function of time. So what is our solution for current as a function of time? It is alpha, which is v over r, times exponential function minus r over L t, e to minus r over L t. We solved the problem. We found the current as a function of time. Now let's plot current as a function of time. At time moment 0, e to 0 is 1. I had current as v over r. And then there is exponential decay. Current as time tends to infinity. Time tends to infinity, current will be 0 in this circuit, which makes perfect sense. We had current, we don't have battery, and the current will be decreasing with time, and if you wait for a long time, then the current will be 0.